Hello and welcome back to Calculus 1, section 2.7 on definition of the limit. So we have been using limit for a week. We had 6 sections involving limit, and finally we are going to learn what it is, right? Which is actually what happened in the history of calculus. Both derivatives and integrals were figured out and used in sciences and so on, and then the limit was defined afterwards. So it was a German mathematician Weierstrass in 1850. So the first paper on derivatives was 1666. So that's almost 200 years difference between the two. So definition of the limit, you need to know the statement, and you need to know what the statement means, because clearly this is what we've been using. So here it goes. Assume that f of x exists for all x in some open interval containing a except possibly at a. We say that limit x goes to a of f of x equals L if for any number epsilon larger than 0 there is a corresponding number delta larger than 0 such that absolute value f of x minus L is less than epsilon whenever zero is less than x minus a less than delta. So this is the definition of a precise definition of a limit from 1800s. Welcome to being 200 years behind. Right? That's better. You used to be 400 years behind, right? So now it's 200 for a little while, and then as soon as we hit 3.1, you're back to 400. So first off, epsilon and delta are Greek letters that are equivalent to lowercase e and lowercase d. So Greeks have a different alphabet. A is alpha and B is beta, and we will have D for the delta, G is gamma, but it's also in a different order, so it's not also order is not one to one. M is ni, M is mu, and so on. So there are they all look different, almost all. So now we see that it's important for you to know that both epsilon and delta are extremely small numbers. You need to think of infinity in terms of being ever-growing number as a concept, right? It's not a number. You can't pin down infinity. You can't pin down epsilon and delta. They are numbers that are extremely, extremely small, right? So they go to 0. So epsilon, delta are as small as we want them to be. two graphs that you have to consider and understand and be able to explain in connection to the limit. So here's some arbitrary function f of x, and I'm going to over here put my value a and the limit L which it produced. So now I'm going to get this tube around. So this value here is a minus delta, and this value here is a plus delta, meaning that each one of these little parts is delta. Now those give off the y values L minus epsilon and L plus epsilon, meaning that each one of these is epsilon here. Now remember the approach. Approach means that you are going towards A. Try mentally to squeeze these in. Hopefully you see that these would squeeze in onto L. Do we all see that? So as you squeeze, now you can squeeze on epsilon, the delta will squeeze into A. You can squeeze deltas, those two red lines would squeeze into L, right? They go together. Because if I come up with another line here after I squeeze, as you can see, it's closer to L on the other side. And as you squeeze even closer, it becomes closer to L. So remember the first sentence I said for limits. Limits are fancy way to compute function value. Fancy way. It's a completely new way of thinking you haven't used right before to compute the function value. But you see that that L is actually just when you plug A into the function. Now limit does much more than that, and we also said that the function does not have to exist at A. Remember the except possibly at A? So we said that the limit can compute even if the function value doesn't exist, where calculations cannot. The second graph is the graph that says that limit does not exist. We can use 1 over x for that. So here's our function. In this case, it's 1 over x, so it's not arbitrary. I could put something arbitrary, it's fine. What happens here? Well, if I am considering 0 to be my A, and then I go a little bit to the right and a little bit to the left to create A minus delta and A plus delta, right, which is the neighborhood of A. Observe what happens to this. These are far apart, right? The y values are far apart. Now, in blue, I'm going to squeeze. But when I squeeze, I'm actually going to draw the new line. So now, the new line. And then when I draw the new line over here, what we see is that on the second A minus delta, A plus delta, the y values are even further apart. So that's the situation when limit does not exist. Over here, limit exists. And it's equal to L. So remember, your epsilon has to be a very small number. Now this epsilon over here, right, it's growing to infinity, right? It's not as small as you want it to be. You can say, I want epsilon to be 0.000000003. You can achieve that on a picture up there, but you can't achieve it on the picture below. So that's the problem. And that takes care of this. Now, the one final thing before we leave, and that is just to alleviate some of my allergies because I've already seen it. Make sure that when you are solving limits, you are using proper notation. So, when you have that the limit of f of x is equal to L as x goes to a, right, that's our way to just write the concept down. Then you will next see limit of, let's say, x squared as x goes to 3. You will compute that the answer is 9. And that's proper notation. If you write this, you trigger my allergies because that is the meaningless statement. That means this over here means nothing. Nothing. Because the proper notation has something always that follows the limit. So this thing over here has no meaning. The answer is 9, so if you have your exam or a lab or something and you have the line, you can just put 9, or you can put the whole thing, limit x squared equals 9, as x goes to 3. But if you put this, it's immediately -1 for notation, and it's per problem. So you can accumulate, you know, -10, -13, -15, just by writing those kind of things. Another one of those is VA equal to 6, right? That also meaningless thing, so we don't do that either. Proper mathematical notation is necessary because this is the only universal language that we have on the planet, that everyone speaks the same way. All right? See you Tuesday.